How old is the universe? Now, in order to figure that question out, astronomers have to measure the expansion of the universe today and then run the clock backwards to the beginning of the universe and then do the math. And the problem is that astronomers have measured the expansion at various times in the universe. And they've done it very accurately. And the problem is that the different measurements disagree with one another. And in fact, the error bars between those different measurements don't overlap. So what's going on? They can't all be correct. One of them has to be right and the other ones have to be wrong. Maybe they're all wrong. Maybe there's new physics that we just don't understand yet. So help me make sense of this. I brought in a ringer, somebody who is an expert in measuring the age of the universe, and that's Dr. Paul Sutter. He actually was one of the physicists who worked with the Planck mission to help perform the most precise measurement in the cosmic microwave background radiation. Paul joins me today. Hey Paul, welcome to the Guide to Space.
Hey, it's been way too long, Fraser. How's it been?
It's good. But I always want to bring you back when there's something that is just like way beyond my pay grade, and we are definitely in beyond my pay grade territory now. So now I set it up, but can you sort of explain the crisis in cosmology?
Right. First off, I object to the whole term crisis.
I figured you would.
But let me explain what's going on. So what we're trying to do is measure the expansion rate of the universe as it is right now at this very instant. What is it doing today? This number is called the Hubble parameter, the Hubble constant, the Hubble value, the Hubble whatever. It's just the expansion rate today, right now. And different ways of measuring this or getting at this are giving slightly different answers, hence this crisis in cosmology.
Right. And if I remember, this measurement is essentially the amount of additional space that is growing between distant objects as they are spreading farther and farther apart. And it's measured in some ludicrously large quantity in megaparsecs per second.
Right. It's somewhere around 68 to 70 kilometers per second, which is pretty fast, per megaparsec. Per every million parsec or 3.8 million light years, or whatever that conversion is, which means for every megaparsec you go out in distance, that particular galaxy is receding away from us an extra 68 to 70 kilometers per second.
And how do we know that number?
So we get at this number for you from a few different ways. One is through nearby supernova. When we pin down distances to supernova and measure how quickly they're moving away from us, when we do this in a sample of galaxies surrounding us, we can directly measure the rate. We can say, okay, there's that galaxy. It's this distance and it's receding away from us this fast. There's that supernova and it's that far away and it's receding away from us at that speed, on and on and on and on, repeat for a few hundred different supernova, and you get the expansion rate around us today. That's one technique.
Right. And now you worked on the team that developed another technique. So how did you guys figure out the age of the universe?
Right, and I was a member of the Planck Collaboration, which is a collaboration using the Planck satellite to measure something in the cosmic microwave background, which is the afterglow light from the Big Bang itself, from the very early universe. What we have is through this leftover light, we can take a picture, a literal picture in microwaves of what the universe was like 13.8 billion years ago, which gives us an exquisite picture, an exquisitely detailed account of exactly what the universe is made of. And from there, once you have all the ingredients in your recipe, okay, I've got this much dark matter, I've got this many neutrinos, I've got this much radiation, I've got that much dark energy. You put all your ingredients together and you run it through your evolution of the universe, which you get from general relativity. No one objects to that part. and you end up with a prediction for what the expansion rate ought to be today.
And what did you get?
The Planck Collaboration gets a number that's a little bit lower than what the supernova results are telling us. And these are tiny differences. The difference between 68 and 70 kilometers per second, or 68 and 72 kilometers per second per megaparsec. But the uncertainties are small enough that it's statistically significant.
Right, and so normally you would hear like one group got 68 and one group got 70, and you say that it must be somewhere in between. Maybe it's 79, but the key is that both groups are certain and the uncertainties do not overlap. And so
exactly.
It's like you have to say that both of them are right.
Both of them are claiming to be right, and so there is a tension here. They both can't be right at the same time, obviously. It's like measuring the average population height and getting 5 feet 8 inches and 6 feet 2 inches with plus or minus 0.1 inch on each measurement. They both can't be correct.
Right. So then what could be the cause of this?
Well, we could be doing something wrong. Maybe the supernova results are incorrect, or maybe the supernova results, their uncertainties, their error bars aren't as small as they say they are. Maybe they should be a little bit wider. And the same thing for the Planck data, the cosmic microwave background data. Maybe it's wrong, or maybe the error bars aren't as big as they should be. So that's one option. Another option is we're getting physics wrong. Maybe our model, our recipe isn't correct. Maybe general relativity isn't the right way forward. Or maybe it's something else. Maybe we're missing something about the nature of dark energy that's changed from the early universe to the late universe that we're not capturing in our models yet.
So then which of those, like I'm imagining, say, a changing amount of dark energy. In other words, the acceleration of the expansion of the universe is changing. How would that explain a different number?
Right. This would explain a different number because in order to get to the Planck cosmic microwave background prediction for the modern day, present day value of the expansion rate, we assume that dark energy is fixed. That whatever it is, we have no idea what it is, but whatever the acceleration rate is, it stays fixed and constant and doesn't change. But if you allow for that amount of dark energy to change, you can get the supernova result if you try hard enough.
Right, and I guess one of the more unsettling consequences of something like that is that maybe dark energy is continuing to accelerate into the future, and we've talked about this before, this idea of the Big Rip, that it tears the universe apart.
Right.
But what are some other kind of less showy explanations that could explain what's going on here?
I mean, this gets into the weeds of statistical analysis, which is where all the fun is, and this is where all the debate is, of do we really believe our data? Is nature lying to us? Are we understanding and interpreting our results correctly? When it comes to the Planck data, the cosmic microwave background, is so accurately measured and so well measured and so precisely measured. And the analysis, and by the way, all the data, the raw data and the analysis is all publicly available. So groups around the world have verified this, that it doesn't look like the Planck Collaboration made a mistake. That there's nothing wrong in the data and that the error bars are the size that the Planck Collaboration claims they should be. Other people have checked the data and it seems legit. So it seems hard to argue against the Planck data being the Planck data. When it comes to the supernova data, however, it gets a little bit messier. Because honestly, let's be frank, stars blowing up are a pretty messy event. And there's a lot of physics that go into stars blowing up that we don't necessarily fully understand. It doesn't make the supernova data wrong, but maybe they're not getting their error bars correct. Maybe they should be a little bit more uncertain in their measurement than they claim. For example, adding the effects of, say, rotation, of maybe some of the supernova are rotating faster than the others, just that is enough to inflate the error bars, inflate the uncertainty, make you not as certain about the supernova results as you thought you were. And as soon as those error bars get big, they can start to overlap with the Planck data and there's no more crisis.
So then what are some upcoming missions that you're really excited about that might help get a better sense of where the mismatch could be coming from?
One path is we need a lot more supernova data. We really need to dig into the physics. We really need to understand the observations. Are we getting this measurement correct? If we're going to assume that the Planck data and Planck analysis are correct, which seems legit, and if this tension really does persist, if we can't figure out what's wrong with the supernova data, if it is serious and it is accurate, and we did nail it, then this tension does exist. We need to figure out what's going on, and what's going on implies new physics. And so what we need to do is look at dark energy and the behavior of dark energy over the past few billion years. And the upcoming missions that are going to tackle this are WFIRST, which is the NASA spacecraft that's going to launch after the James Webb. So, when our grandchildren can work on it, if we're estimating NASA timescales
come
correctly.
on. No, it's going to launch. It's going to launch.
I went there.
Yeah,
It'll launch eventually in 2137.
Yeah. Oh.
And the Europeans also have Euclid, which is the equivalent to WFIRST. And there's also a bunch of ground-based surveys like the LSST, the continued BOSS surveys. There's a bunch of galaxy mapping surveys that are trying to get a handle on the behavior of dark energy over time to see if it really does change.
Right. So stay tuned. We should watch this unfold. And I think the last thing is I just want to get, for you as one of the people who worked on that, and it's possible in your book, you were pretty happy with how well that measurement had been made. Finding out that there is still uncertainty, how does that make you feel?
This is the nature of scientific exploration. The supernova data and the Planck data and all the data 5-10 years ago were good enough to confirm that yes, dark energy exists. Yes, the Big Bang model is correct. As we make continued observations, as we get finer and finer data and better control and understanding of what's going on, the error bars shrink. And when these different probes don't quite align, when the puzzle pieces don't quite fit, this becomes very interesting. No matter what, we're going to learn something. It could be we just learn about how supernova work, which is awesome astrophysics, or we learn about how dark energy works, which is also awesome astrophysics. So no matter what, we're going to learn something from this.
Yeah. It's that idea that whenever scientists figure out that they might be wrong, they love it.
This is fun.
More mystery. This is fun.
Finally, we have something to talk about at the conferences.
Yeah, something to disagree about. All right, Paul. Well, obviously, keep us posted. Let us know when you know what the next best answer is.
Absolutely.
All right. Thanks, Paul.
Thank you.
Now, if you want to check out more of Paul's work, you should check out his YouTube channel here. Also, he's got an incredible podcast where he covers all kinds of topics like string theory, physics, the best kind of cheese. And Paul's also written a wonderful book called Your Place in the Universe, and I'll put a link to all of these things in the show note. What do you think? Let me know your thoughts in the comments. Here are the names of the patrons who support us at the $10 level and more. Want to see your names here and support the work we do? Go to patreon.com/universetoday. Once a week, I gather up all my space news into a single email newsletter and send it out. It's got pictures, brief highlights about the story, and links you can find out more. Go to universetoday.com/newsletter to sign up. Did you know that all of my videos are also available in a handy audio podcast format, so you can have the latest episodes as well as special bonus material like interviews with me show up right on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts, and I'll put a link in the show notes. Want more information on this fascinating topic? We did a video about new research that says that dark energy could be changing over time and what the implications might be for the future of the universe. Check it out here.